So thank you so much, Milind, for this opportunity that we can actually host you, and for your time. I know it's late there, and this lecture is organized as a part of the course in RMIT AI and Data Science professional course for Masters of AI and Masters of Data Science, and thank you for Lawrence. Thank you to Lawrence for organizing to organize this with Milind. And also this talk is cross-promoted at the School of Computing Technologies at RMIT, and also cross-promoted to the Center of Excellence on Automated Decision Making and Society. It's actually the first talk in our Tech Talk series. So thank you for kicking this off, Milind. So I'd like to hand this over to Lawrence to introduce Milind.
Hi, it's an absolute honour, pleasure, delight to introduce Milind. You know, it's very generous of him to make this time to come and present to us. We know it is late over in his side of the world, but I've known Milind for more than 20 years. I had the pleasure of visiting his lab and his students and research staff over 20 years ago, which, as Flora says, starts to date me, but also dates Milind. But Milind is a superstar in the multi-agent systems and the general AI field. I mean, he's a world-leading researcher. His earliest known research won many awards for modelling teamwork in multi-agent systems and leading to much more robust multi-agent systems. And he, like I said, he's won awards for that. He was the Ichikai John McCarthy Award winner just a few years ago. So he's a leader in the whole AI field. He was previously at the University of Southern California and its associated Institute ISI, and which I forget, Information Sciences Institute. He was a lab leader there, but he more recently, a few years ago, moved to Harvard, which was, of course, just a recognition of his leadership. So he's a professor there of computer science, and he's also a director of AI for social good at Google Research India, which is, again, just an acknowledgement of his standing in this field and this new area, which he's been a leader in developing, of applying AI to social problems and, problems of benefit to the whole of society. So focusing on issues like conservation, public health, social work, and public safety and security. So it's, like I said, it's a delight and an honour to have Milind come and talk to us. He's not going to, I guess, go into the depths of some of the sophistication of the technology he's going to build, but he's going to certainly talk about the applications of AI to addressing some of the great problems in society in general. So again, welcome, Milind, and sorry we can't pair this with a cricket game for you to enjoy, as you usually like to do when you come to Australia, but hopefully we'll be able to do that in not too distant a future. And you're always welcome here, physically and virtually like now. Thanks.
Thank you. Thank you, Lawrence, for what a generous, really terrific, generous, warm introduction. I'm very grateful for that. And I visited RMIT indeed in 2015, and it was an awesome visit. It just happened to coincide with the Cricket World Cup at the time. So, but fantastic, fantastic visit. So I'm going to talk to you today about AI for social impact. For the past 15 years, me and my research team have been focused on applying AI and multi-agent systems research towards public health, conservation, and public safety and security, with the key challenge of how to optimize our limited intervention resources. And I'll just get down right to some of the lessons that we have learned. The first lesson is achieving social impact and AI innovation go hand in hand. So, concrete example is work we've done, which I'll cover today, in reducing HIV amongst youth experiencing homelessness in Los Angeles. We are living through one pandemic, which is the COVID pandemic, but there are other pandemics, for example, HIV. Harnessing the social networks of these youth, we are able to show that our algorithms are far more effective in reducing HIV risk behaviors among these youth compared to traditional approaches. What this work required was innovation in the area of social network algorithms and so-called bandit algorithms. With respect to conservation, we have large conservation areas to protect limited ranger resources. Concrete example of work I'll cover here, work we've done in Uganda and Cambodia. Harnessing past poaching data, we are able to predict where poachers may set traps, and for the past several years have been able to remove thousands of these traps. This has required advances in combining machine learning and game theory in so-called green security games. In the past, we've contributed newer algorithms in game theory in a model called Stackelberg security games. This is for counterterrorism, and this was work done in collaboration with the US Coast Guard, for example, which have been using these algorithms we developed, or with the Federal Air Marshal Service and other security agencies in the United States. A second lesson is all of the work I will talk about today is in partnerships with non-governmental organizations, nonprofits, and some government organizations. I'm often asked, how do you start this work on social impact? And my answer is that the work we do is inspired by the work, that's tremendous work that the nonprofits are doing around the world. And our goal is to empower these nonprofits to use AI tools and avoid being gatekeepers to AI technologies for social impact. A third lesson is in doing this work on AI for social impact, we have to pay attention to the entire data to deployment pipeline. It's not just about improving algorithms. So our work starts by immersing ourselves in the domain with the nonprofit, trying to understand the kind of problems they face, the kind of data they have. Following that, a predictive model, a machine learning model, makes predictions on which of the cases the nonprofits has are high risk versus low risk. If we had enough resources, we would have intervened on all of the high risk cases, but we don't. And so which cases to actually intervene on given limited resources, that's the job of our multi-agent reasoning algorithms. And then finally, field testing and deployment is crucial because social impact itself is a key objective of our work. If we are not achieving social impact, then it is not AI for social impact. So in the rest of the presentation, I'll start with public health, then go into conservation. I'll cover papers from 2017 to now. I'll highlight the role of the key PhD students and postdocs by putting up their picture in the top right-hand corner of the slides on their work, where their work is shown. So I'll start with this social work on social networks. This work is motivated by trying to prevent HIV amongst youth experiencing homelessness in Los Angeles. There's 6,000 youth who sleep on the streets of Los Angeles every night. The rates of HIV amongst this population is 10 times the rates of the normal housed population. So homeless shelters will they cannot obviously communicate with all 6,000 youth. So they try to bring in some key peer leaders, educate them about HIV prevention, and expect these peer leaders to talk to their friends and their friends to talk to their friends. And in this way, information to spread in their social network. This is real face-to-face interaction. This is not happening, for example, over Facebook. Now, some of you may recognize that this is the classical problem of influence maximization in computer science. The input is a social network graph. We have to choose some K peer leader nodes in this graph, say 5 peer leader nodes or 50 peer leader nodes, so as to maximize the expected number of influence nodes, maximize the expected number of youth who know about HIV prevention. We assume here that information spreads in so-called independent cascade model, and I'll explain that to you next. So given some social network, remember this is not over Facebook, this is the actual friendship network. This is an actual network of the youth in one of the shelters in Los Angeles, friendship network. And each number here, in order to protect the identity of these youth, we've just given them a number that represents a single youth in this network. So if we pick one youth, let's call this youth A, then educate them about HIV prevention. Then in this independent cascade model, we assume that there is friend B who will know about HIV prevention with a probability of 0.4. And then B will talk to C, their friend, with a probability of 0.4. So C will also come to know about HIV prevention with a probability of 0.4. And so information is cascading in the network in this fashion. So if we are given a budget of 5 nodes, now we have to select which are the best 5 nodes, which are the best 5 youth to select in the network to maximize the spread of HIV information in this network. So is it this 5 or is it some other 5? That's the key challenge. Once we select these youth, then our social work colleagues, as shown here in this picture, will, there's a day-long session they go through about HIV prevention and how to spread this message in the network. So that's a picture of this education session in progress. So that's the challenge that we face. Now, there are standard techniques in computer science for doing influence maximization, but if we try to apply them directly in our work, there are 3 key challenges that come together, and they arise because of lack of data and uncertainty. Now, often in the domains we face in AI for social good, lack of data is actually a feature. It's just the way it is. I've seen students who work with me who will complain that they want to do data science, but there's not real, clean data sets available in these kinds of domains that we work with. We're working with marginalized communities and so on. And that's just the way it is. We have to work with the fact that we have limited data. And so one of the challenges as a result is that we do not know the exact propagation probability, like 0.4. We don't have immersion in this domain clearly shows it is hard to get those exact probabilities. Peer leaders themselves sometimes don't show up. So we may say we want to select these 5 youth, but these are youth under difficult circumstances. So we may have selected a youth, but that youth may not have a bus fare to come to the shelter to go through the session. They may send their friend, for example. So we have to handle this peer leader no-shows. And thirdly, normally in computer science, when this problem is studied, they assume that the whole social network is given as input. But in our domain, we do not know the social network ahead of time. All we can do is ask a few of the youth who their friends are. We cannot ask it of the entire set of youth. So we may say, we can go to a shelter and in one day ask 20 youth about who their friends are, and in this way uncover a small fraction of the social network. But that's all we get. And based on that, we have to figure out who are the key influencers. So again, these are challenges that we just have to address in our domain. I'm going to just sketch some ways we solve these problems. I'm not going to get into some of the details. If anybody's interested, I'm happy to have a conversation later. But hopefully at least it gives you some intuition about how we solve these problems. So I'll refer to a couple of these. So for example, uncertainty over propagation probability. Normally in influence maximization, as we discussed, it is assumed that if we talk to a youth C, then an adjacent youth, their friend D, will get informed with a probability of 0.4, which is known ahead of time, about HIV prevention. In our domain, this probability is not known. So we can say that we are sampling this from some distribution, but we may not even know the mean of this distribution. So therefore we can say the mean of the distribution lies within some interval. So now we are faced with the problem of influence maximization when there's uncertainty in the propagation probability. And this problem we handle by, basically this is a problem of robust influence maximization. We solve this problem as a game. So on the one hand, our algorithm is trying to choose peer leaders to maximize the spread of influence. But we assume that nature is trying to choose parameter settings, is trying to choose those propagation probabilities to cause our algorithm to perform as worse as possible. And so for those who are familiar, we're basically trying to solve this as a zero-sum game against nature, where we are trying to maximize the payoff. Nature is trying to minimize the payoff, and the payoff is measured as a measure of regret, a ratio of the outcome of the policy that we have chosen to what we could have chosen optimally had we known nature's parameter settings in advance. So I'm not going to go into details, but basically by solving these kinds of algorithms, we can get a robust policy. The second problem I'll discuss is sampling of social networks. We could imagine sending our social work colleagues to a homeless shelter, they can sit there for days, they can talk to all of the youth and figure out the entire social network within a shelter as to who's friends with whom. This is very costly, and if we want this work to be applied in different cities in Los Angeles, San Francisco, etc., then this is not going to scale up. We need a fast, simple way for this technique to work. And to that end, we assume that we can only query, let's say, 15% of the nodes. We can go get our social work colleagues to go to a homeless shelter, ask questions about, say, 15% of the youth that may show up in the center that day. That's it. And they'll ask a question of who are your top 5 friends, something like that. Just note that down. That allows them to essentially get understanding of the social network. The key here for us is the right sampling algorithm. Who do you sample? That's the secret sauce that we bring to the table. And so the idea is that once we sample exactly this small fraction of the population, then we output the K peer leader nodes. And at the same time, we guarantee that the performance of our algorithm, even though we have chosen peer leaders from a small sample of the network, is similar to the optimal possible if we knew the full network ahead of time. And this is done by sampling nodes randomly, estimating sizes of their communities, and then choosing seeds from largest K communities. There's the AAAI 2018 paper, should you want to get into details of how this gets done. All right, so having addressed some of these challenges, we built a system that I'll refer to as sampling healer. Sampling because it's sampling the network. It is generating a robust policy. And what it does is it selects a set of peer leaders. It says, bring in these 5 leaders, these 5 youth. And then after seeing who's present, who's absent, it will say, bring in the next 5 youth and so forth. So at this time, it was time to do a pilot test. So with the sampling healer, in each, there are 3 arms to this pilot test. Sampling healer, which is our sampled network. This is our actual algorithm. We recruited 60 youth. Healer is just like sampling healer, except that it knows the full network, doesn't have just a sample of the network. And degree centrality is the traditional approach. Bring in the most popular youth. It makes sense, right? To bring in the youth with the highest degree, the high degree centrality. Again, about 60 youth in that. And we then selected 12 peer leaders in each case as per the recommendation of that algorithm. And this is an actual picture of our social work colleague educating the youth who were identified as peer leaders by these algorithms. There were obviously 12 different peer leaders in each of these pilot tests. And then the question was, at the end of a month, how many of the non-peer leaders, the ones we did not bring in for the education session, got informed about HIV? And what we find is after a month with degree centrality, 25% of the non-peer leaders got informed about HIV. With healers, 75% of the non-peer leaders got informed about HIV. So our influence maximization algorithm is clearly far more effective in spreading HIV information compared to traditional approaches. With sampling healer, we seem to be even higher than healer. And that just could be this particular sample that was chosen because we are doing a small pilot test at this point. But given the performance of sampling healer, we decided to now compare it on a larger sample. So in this actual final test, we are not only interested in the actual how much information was spread, but whether there was actual change in behavior. And this is work done with Professor Eric Rice of social work. As far as we know, this is the first large-scale application of influence maximization in social networks for public health. And this was done with in collaboration with 3 nonprofits: My Friend's Place, Los Angeles LGBT Center, and Safe Place for Youth. We recruited 750 youth in this study, 250 in each of the 3 arms. The first arm was our sampling healer algorithm. The second was degree centrality. The third was no intervention at all. In each case, we recruited peer leaders as per the recommendation of the algorithm. 15% of the youth were chosen as peer leaders in each case. And then we wanted to understand what was the change in behavior after a month and then after 3 months. And here's what we found. At the end of 1 month, in terms of reduction in condomless anal sex, which is one of the HIV risk behaviors, with sampling healer, there was more than 30% reduction in condomless anal sex. With degree centrality and control group, there was no reduction at all at the end of 1 month. At the end of 3 months, we see that degree centrality begins to catch up to sampling healer, but still sampling healer is still better. What's important here is that the speed at which sampling healer is able to cause changes in behavior is important because this is an HIV risk behavior. So having this behavior change occur faster is important. And also because youth in this community come and go, and therefore having this behavior change happen faster is important. We also look at a second HIV risk behavior, reduction in condomless vaginal sex, and again, sampling healer is seen to perform better. Our colleagues were clearly happy with these results, our collaborators. I hope this video will play.
The audio not working, so I think that tricked the toggle button again.
All right, okay. Fine. I guess I'll just move on. So the next step here is, for those who may be familiar with reinforcement learning, we have been exploring uses of reinforcement learning for influence maximization rather than our hand-drawn algorithms, and shown that it in simulations performs better, but to test it out in the field is an exciting area for future work. So I'm going to go through a couple more areas of work for about next 10 minutes, and then I'll stop and take some questions. So I'll move on to health program adherence. So remember that we have this data to deployment pipeline. So first stage is collect the data and make a predictive model, making predictions of which of our cases are high risk versus low risk. So here I'm going to look at work that we've been doing at Google Research India on maternal and child care. A woman dies in childbirth in India every 15 minutes. 4 out of 10 children are too thin or short. We are very fortunate to be working with a nonprofit called RMIT, which has 18 million women enrolled. One of their programs is called M-Mitra. Basically, it's a weekly 3-minute call in a local language to a new or expecting mom. So it may be a call that says in 3 minutes, you know, you are in 6th week of pregnancy, you should take this type of health supplement. And they have shown that in randomized control trials, this program leads to significant benefits. So women who listen to the 150 calls that come in, they have significant benefits to them and their children in terms of health compared to women who don't listen. 2.2 million women have enrolled in this program. So one challenge, unfortunately, RMIT faces is that women enroll, and then 30% or so, 35% of these women will become low listeners or drop out of the program. So the first job in terms of prediction is, can we predict which beneficiaries, which of these women are going to drop out? So if we can predict who's going to drop out before they drop out, then RMIT can call them live or go to their homes and persuade them to not drop out of the program. So here's how this is supposed to work. You have mom number 1. She does not pick up the automated voice call about health in week 1, but yes in week 2, yes in week 3, yes in week 4, yes in week 5. Mom number 2 picks up the call in week 1 and 2, but not in week 3, yes in week 4, not in week 5, and so on for hundreds or thousands of these women. It turned out that in this particular case, mom number 2 and 4 dropped out of the program. If we could inform RMIT ahead of time before they drop out that mom number 2 and 4 are at high risk of dropout, then Arman can do live calling or other ways of trying to prevent them from dropping or persuade them to not drop out. So we built a classifier. We did a test with 18,000 beneficiaries. This was done in fall of 2019. We made predictions, and indeed in the spring of 2020 verified that women who we had predicted drop off, we have a high recall, a high precision, more than 0.8. And so this seemed like a good system in terms of making predictions about who's likely to drop off. Okay, we can make predictions, but is that really helpful? So we did another test to actually intervene, to engage in phone calls, live calls with these women to say, persuade them to not drop out. And it turns out that our call intervention indeed causes 44% of these women from stopping them from dropout, as opposed to the control group, which in this case is about 22%. So this identifying women at high risk and calling them and preventing them does seem to help. Unfortunately, what we still have is that, and this is really in service of helping these 300,000 beneficiaries. 30% of 300,000 is 100,000 beneficiaries. And so if we say to Arman that, well, we've identified 100,000 women at high risk, now you figure out who to call, that's not going to work. So we have to prioritize exactly who to call week by week. That's what I'm going to talk about next. But before I go there, let me introduce another domain. This is tuberculosis. It causes 500,000 deaths in India every year. 3 million are infected. And one of the challenges is to cure TB, a person has to take this medicine for 6 months. And this has got a lot of side effects. So people don't want to take it for 6 months. They start, and then after a while, they'll drop out of treatment, which is bad for them and bad because it also leads to drug-resistant bacteria. So again, there are these phone systems to try to track who's taking their medicine or not. And again, we can make predictions based on these phone call patterns as to who's at risk of drop-off, so that there can be early intervention before they drop out. With data from a nonprofit called Everwell, with 15,000 patients and 1.5 million phone calls from these patients, we are able to show that our prediction algorithms are more effective in terms of identifying who's at risk of drop-off compared to the rule-based system that this nonprofit had. Okay, so as I said, we've made a prediction, but we may have predicted and identified 100,000 women who are at risk of dropout. And how do we actually then decide who to call? Because you cannot call 100,000 people very quickly because we have limited resources. And so here's a challenge. You can imagine that you have a health worker who has a large number of high-risk patients under her care, and she can call only, say, 10 patients per day. Which 10 patients should she call? So you can imagine in the TB domain, she chooses the first 3 patients, calls them saying, hey, did you take your medicine? And the first 2 say yes, the last one says, no, I didn't take my medicine. Then she encourages them to take their medicine, and now she has to decide which 3 patients should I call tomorrow. And she has to keep doing it every day for 180 days because the TB treatment is 180 days. And so you can imagine this health worker trying to figure out who to call every day. And there's a particular recommendation to do this in a round robin fashion, call the first 3, then the next 3, then the next 3. But that's wasteful because there may be patients who are taking their medicine regularly, and you just keep calling them again and again when they don't need to be. And there are patients who really need more calling, but we are not calling them because their turn hasn't yet come. And so these kinds of problems of figuring out who to call can be addressed in terms of what's called a restless bandit model, where each arm of this bandit is a patient, and we have 2 states, whether they're adhering or not. Again, I'm going to skip over a lot of details here because this restless bandit model is would require a lot of time for me to explain details, which may not be as interesting. But we have techniques to solve this problem so that there's more efficient policies. And in simulations, in this case, this is not real, the simulations, we have shown that our algorithm compared to baseline, so the baseline is shown in orange, our algorithm is in blue. you can see that our algorithm is much faster than the best baseline without losing much in terms of solution quality. All right, so what's exciting here is we have a 20,000 subject trial ongoing in India. So every week we recommend who to call in terms of these beneficiaries to Arman. They call them and they give us results as to what happened. And so we are comparing our algorithm for restless bandits with a baseline, which is based on round robin, and then a third arm where there's no intervention. And we expect these results to be available very soon. And so it'll be exciting because it's the first large scale application of restless bandits, certainly in the area of public health. So I'll quickly cover a third topic and then I'll stop for questions. This is agent-based modeling for COVID. So in March of 2020, at least in the United States, everything started shutting down due to COVID. So as an agent-based modeling group, we started looking at agent-based modeling for COVID-19 dynamics first. And this is an article that appeared in the Proceedings of National Academy of Sciences. Next, in our AAAI 21 paper, we looked at tracking disease outbreaks. So if you imagine it's Harvard or it's RMIT, and you're testing students to see if there is an outbreak of COVID, and you sample a small fraction of the students and you get noisy data of their tests results as to who's positive, who's not, and you're trying to figure out is RT, the R reproduction rate, is that going above 1? The traditional epidemiological tools to do that, we showed compared to them that our new approach provides much more accurate tracking results as shown in this case. But the work that I thought I would cover a little bit more is this work with Professor Michael Mina in Harvard School of Public Health on COVID testing policy. So there are a range of tests that have entered the market with varying sensitivity and cost. Everybody rushes to the PCR test, which is a gold standard. Basically, it detects very low viral concentrations, but the cost is high and it takes at least 24 hours to get results back. Antigen strip requires higher viral concentrations. It's less sensitive, but has a low cost, and you get results back quickly, even in 15 minutes. And so question is, again, if you're Harvard, you're RMIT, or you're some kind of campus, what test should you use? So you can imagine the model here is that we test all of our students, and then whoever is positive, we isolate them. And we can do this either by using our less sensitive antigen strip on every student or the more sensitive PCR test. So if we could do both sorts of tests with equal frequency every 3 days, and you get results back instantaneously and isolate the student who or the individual who tests positive, then it turns out if you can indeed do this, you get the results back quickly and do this equally with equal frequency, then indeed the more sensitive PCR test is better. Because on the y-axis here is total number of infections, and with the less sensitive test, more people get infected. However, if we just again go back to the fact that the more sensitive test, there is a delay in getting results back, a day's delay, for example, then all the advantages of this more sensitive test are lost. There's more than there's a significantly higher rate of infections with the more sensitive test. Furthermore, because of cost, if we can run the more sensitive test only every 5 days instead of every 3 days, again, all the advantages of the more sensitive test are lost. So the key result of this modeling was that rapid turnaround time and frequency is more critical than sensitivity for COVID-19 surveillance. This result turned out to be picked up by New York Times and Washington Post and many other places. We were very delighted that Dr. Anthony Fauci talked about this paper. This was a great honor. And of course, our collaborator, Dr. Michael Mina, is consulting with the Biden COVID Task Force, President Biden's COVID Task Force. And so we give all credit to Michael Mina, of course, but we think our modeling helped him make this case to advocate to FDA and CDC that this rapid test really work. And today, as a result of his advocacy, rapid tests are now available in pharmacies locally so that people can use these tests in their homes and isolate themselves. So stop here and take questions, and then we can, take questions for about 3-4 minutes, and then I'll do about 10 minutes of talking about conservation. Okay, so I'll stop for questions. Please go on.
Well, it's been brilliant so far. There are a couple of questions already on the chat, and let me just Sneha have got a question. I'm just wondering which project you're referring to, Sneha. How long did it take to come up with the algorithm after you got a data set in hand? Maybe if you could clarify which project. Okay, let's get back to that question later on. That's the second question about the drop-off from Michael. I think this was to do with the TB. What were some of the inputs used to identify who will drop off? Was this NLP from calls or general information about a person? So features.
So I think the more important features in the TB domain was the particular pattern of calls. So, they basically, you have information as to the duration of the call every day and whether the call was picked up or not. So you can imagine that that's the information we have. So it's today this person, called at 9 a.m. and the call lasted for so much time, something like that. Tomorrow, the next day, we didn't get any call at all. Third day, we got a call, it was at 11 a.m. So we have this kind of information about the call, and that's what gets used in making predictions. We have also looked at using demographic information, at least in the TB case, and it helps somewhat, but the calling pattern is more important to make predictions. In the other case, which is the Arman mothers dropping out, there it's the demographic information is actually quite useful in addition to the call patterns in order to improve the accuracy of making predictions.
Great, thank you. So there's another project. There's another question about, I think it may be to do with simulation in general. So how would you model the real world entities, especially in a very dynamic environment? What are the steps to make sure the model is generalized?
So I guess this probably refers to our COVID-19 simulations, which are the ones that I mentioned in terms of, campuses and so forth. And so there, for example, in our paper that I mentioned here for agent-based modeling, essentially we are really trying to get at those elements that are relevant for the particular disease spread. So in this particular case, there's a contact matrix of people in terms of who talks to whom with what frequency. We have household general information about the sizes of the household, and then in the household we assume that there is frequent contact. And so in this agent-based model, there was we modeled entire cities, we modeled families. The families had we have people who are going to work. At work there is a certain contact pattern, and so we have information about just from normal surveys that is available about the contact that may happen at work. And so all of this kind of information gets taken into account in order to build this model. And then, there are more details here about how the infection spreads and so on. But in a sense, in all of these simulations, we are trying to make sure we abstract out things that are not important and only keep those things that are important, in this case, for example, for disease spread.
Great, thank you. I got a question to do with the influence maximization paper. So sure. It's this really great work, and I'm actually curious to do with your randomized control sampling, because you mentioned you could only sample a few, not all, right? And you want to maximize that also. So how did you ensure that although the goal is to maximize influence, but what about if there's another objective, which is to reduce bias in sampling, right? How would you deal with that? So that is one question I have. And the second question I have is to do with the behavior change tracking. So how did that happen? Is that is someone asking them the changes over time? And I really like the fact that you're actually asking 3 months after the intervention as well, because a lot of behavior change study, they only did the first 1 week or 3 weeks and then it went off.
Right. So with respect to bias in sampling, so we have in this work done analysis to try to figure out if it is the case. There are different kinds of racial groups. There are groups, there are black, white, Hispanic, mixed race, all of that, and whether the influence was spread, without much difference. Basically, if everybody got a roughly similar proportion of influence. And so for the networks that we had, we did not have disparities along racial groups or gender and so forth. However, we have networks which are not part of our particular study, but other networks where we can show that indeed there can be significant disparities along racial groups, for example, in terms of benefits of influence maximization. And so the question you raise about bias, so how to sample to make sure that there are no such disparities, is actually an important one. And it's an area of future work. So we have done work when the network is known for fair influence maximization, but when the network is not known, how to ensure that the benefits of influence maximization are spread in a fair way across different communities. That's an important open question, has not been addressed in the literature. With respect to behavior tracking, we engage in normal social work practices in order to engage with the youth. So basically, behavior change is tracked by them voluntarily giving this information, but the information is given is done via computer. So basically, it's a computer interface. It's not some person asking them to reduce bias, so that they don't feel like they have to give a favorable answer. So there are other kinds of standard social work practices used in order to understand or in order to track this behavior change of youth.
And I just remember one thing to do with that also, with your randomized control trial with the three different methodology, whether you're using your sampling method or degree centrality. How did you separate the groups there on a control and treatment group?
So basically, these are 3 separate shelters in 3 different parts of the city.
Okay.
And then we collected, so there's 250. So basically 80 youth from one center, 80 from another, 80 from another. This was done. So the youth, actually, the whole population roughly changes every 6 months or so. The whole population begins to change. So we did this once in January. Then, 6 months later, July, August, again, you recruit 80 youth in each of the 3 centers. And then again, 6-7 months later. And so this was the whole thing lasted for about 2 years in order to track this. So basically the youth are very, basically there's a completely different youth communities that get engaged. And also when we recruit, we make sure that the youth who are recruited have not engaged with us in the past. So there are all these safeguards trying to put into place to make sure that there's no contamination, and also everybody, all of the different arms got a chance at each of the 3 different places, at each of the, in 3 different time slots and so forth. So everything is equitably spread across the 3 arms of the experiment.
Excellent, thank you. Just wondering if you have time for 1 or 2 more questions before we move on?
Sure.
Elham, you've got a question. Do you want to just to turn on your microphone and ask this question?
Yes, thank you. I mean, now I might misuse my opportunity and ask a different question as well. But I think when you were talking in the RMIT project about women receiving a call and trying to just kind of make them stay with the program, my first reaction was that if I would receive a call to encourage me to stay, I will definitely leave. And I just kind of like, I was just thinking, would it be possible to just kind of like change the model in a way that the content of the conversation and the potentially emotional reaction to that can be just kind of like reflected in that 0-1 type of model that you had the rest expanded?
That's an excellent question. So what happens is that this, these are trained callers who are calling from hospitals to these mothers, and there are, let's say half the women or something like that may not pick up. They make 3 tries to try to get to the moms, and they engage in like an extended conversation with these mothers. And so you're absolutely right that this is a sensitive conversation. And so some mothers will say, hey, you've been calling me at the wrong time slot. I'm busy at that time. You have to change when you call, something like that. And so some of these cases get resolved in terms of there's some kind of technical difficulty, like the calling time is wrong, or the phone number is whatever was registered was the husband's phone number, and it really should have been the wife's phone number or something like that. So some of these difficulties get resolved. There is a certain component where a woman unfortunately has lost a child. And in this case, this call is important because otherwise there's this traumatic experience of this automated voice calls keep on coming. And so this is a benefit. But what you're saying with respect to other reactions that the women may have of annoyance and then leave, that's an interesting one. And I should talk to Arman to see what their reaction is to understand what actually happened.
My expectation was that, okay, so the trained nurses, they would deliver standard call, but the reaction to those standard calls can be different, and how we can model that. That was basically what I was just thinking. But
good question, and we haven't done that work.
I would misuse this opportunity. Do you have, I know you shared your 3 lessons at the beginning, but just for someone who's young and wants to start, what would be a way of approaching NGOs and convincing them that you can do the job that they want to? Because they have to share their data and it's pretty sensitive. So that's, I just thought, if you have any more kind of like advice, that would be appreciated. Thank you.
Absolutely. No, thank you for all these very important questions. So I want to offer a few pointers with respect to starting this type of work. One, at Google Research India, we have a program for matchmaking. So basically, we come out with a call. We came out with one in 2019. There was one in 2020. There'll be one in 2021 again. So essentially, we invite university researchers from around the world to apply to the program. We invite NGOs to apply simultaneously. So last time in 2020, there were 180 faculty members, researchers from around the world who had AI expertise who applied. We have 150 nonprofits who applied. And then we did matchmaking. So every nonprofit got to meet with 3 AI researchers. Every AI researcher got to meet with 3 nonprofits. And then they came up with a proposal after their meeting. And then we are, essentially going through the proposals, and then we'll select 25 or 30 of these teams. We'll fund the NGO, we'll fund a faculty member to go do this work jointly. So this is one avenue, to sort of be introduced to an NGO and continue, start the work. So that's one thing. Another possibility, which we've done locally here at Harvard, is that we just invited NGOs to our university, and then basically we invited our few researchers to be in the same. Now it's all in Zoom, so it's not physically in the same room, but basically on one Zoom call. And we did breakout rooms, and again, same thing, matchmaking. And then finally out came some projects after some discussion. And so that's another possibility. But I agree with you that if you just go to an NGO and say, so I've had these students who, after this one meeting in the breakout room, they say, yeah, we'll work with this NGO, and then they expect that the NGO is just going to give them everything in one shot. So it takes, I agree with you that it requires some kind of relationship building and so forth. But, you know, it has, you know, maybe you talk to 2-3 NGOs and not everybody agrees, but there'll be one of them who will say, sure, they have this problem, they have this data set, and there is, after some kind of relationship building, they'll say, sure, let's you know, let's work together. I wonder if you know, via this class, I've also actually in my class on AI for social impact here invited NGOs to come and lecture in the class, and then allowed, you know, have students talk to the NGOs and form projects that way. And so that might be another avenue. So I wonder if you know, this particular class that you're part of could invite NGOs, and maybe that's a way to build relationships. So I don't know, these are some ideas I have. I'd be happy to discuss more. It's such an important question.
Excellent, thank you. We have a hand raised. Harvinder, do you want to have a quick one? Or maybe we can continue and get it, sure. Get the Harvinder to come in at the end.
Yeah. Hi, Milind. Hi, Flora. So I'm not sure whether this question is already answered, but my question revolves around on the fact of the HIV.
Sure.
And the question is, on what basis and features or background study did your algorithm predict or choose the best volunteers or peer educators for the HIV? And secondly, on the same context, how did you keep in touch with everyone and see if the volunteers are doing their job to their best?
So with respect to the second question, we have in this case, like, you know, 250 youth who are recruited as part of each arm of the experiment. And so we know who they are because they have, you know, they have been recruited, you know, obviously with all the IRB approvals and everything into the experiment. So we know how to contact them, and we can follow up with them and so on. So it's just part of the study that all of these youth are part of the study. So it is easy to follow up with them in the sense that we know who they are and so on. Of course, there's some attrition, some people leave the city, all that, but otherwise, you know, we have their contact information to follow up with them. With respect to identifying the volunteers, the peer leaders, that was the algorithm that you know, is trying to find the key peer leaders by sampling the network and then figuring out who's the best peer leader by that, you know, robust influence maximization, by playing a game against nature to figure out who are the best people to spread information. And so that's sort of our algorithm to figure out who are the best peer leaders. Hopefully that answers your question.
Yeah, it does. Thank you very much.
Thank you. Wonderful. So let me proceed at this point. I'll spend about 10 minutes just giving you a quick overview of some of the work that we've done in conservation, and end with some of the lessons that we've learned. So, you know, around all over the world in conservation areas, there are wonderful wildlife, but there are threats to the wildlife, snares or traps by the thousands that are placed in order to maim and kill wildlife. So you can imagine the job of a ranger to search these forest areas, trying to look for traps. And you can see that this is a very difficult task if you have a very small number of rangers who are in charge of thousands of square kilometers of national parks that they have to protect. So for example, this is the Queen Elizabeth National Park in Uganda, where we've done a lot of work. And so in order to figure out where to send rangers, you can divide up the park into 1 kilometer by 1 kilometer grid square. Each grid square now is so-called target. Areas where there's water, you can imagine there are more animals, so this is a more important area for poachers. So we are trying to learn poacher response model at each target to figure out how they respond to our patrols. So based on that, we can recommend patrolling strategies to these rangers. So we have 14 years of data from Uganda when we started this work. So for example, it has ranger patrol frequency per each grid square, animal density per each grid square. This obviously we know from maps what is the distance to nearby rivers, roads, villages, etc. And so based on these different features, we are trying to predict the probability of finding a trap per 1 kilometer grid square of the park. We did do this prediction using an ensemble of classifiers. In the interest of time, I'm going to skip the details of that. We produced all kinds of results in the lab to show recall, precision, this, that, AUC, what, it doesn't matter. Our colleagues in the field are not convinced. They wanted to do an actual field test. So we selected 2 9 square kilo. This is our first pilot test, 2 9 square kilometer areas in Queen Elizabeth National Park that were infrequently patrolled. These are shown by the green dots. The red dots are where previously a lot of snares, traps had been found by the rangers. We are asking the rangers to go to completely new areas, very infrequently patrolled. They haven't found any snares there. And we told them, once you patrol them, our model predicts you're going to find snares there. And so the rangers patrolled for a month, and every day they would report back an email as to what they saw. Initially, there was nothing, but then they found a poached elephant with its tusks cut off. And soon thereafter, a whole elephant snare roll, as pictured here, that they removed. So poachers were active in the area. They were killing elephants, but before they could kill the next set of elephants, we were able to remove this elephant snare roll, hoping that this would, we are hoping that this has saved lives of elephants. Then we had 10 antelope snares that were found and removed. So this pilot test was seen to be a success. And at this point, there was a longer test that was done in Queen Elizabeth and Murchison Falls National Parks in Uganda and Sri Pak Wildlife Sanctuary in Cambodia. In each park, we selected 24 areas, infrequently patrolled areas of 9 square kilometers each. We predicted some of these to be high risk, more snares will be found. Some of these to be low risk, less snares will be found. So basically, we are not saying go to any, infrequently patrolled area and you're going to find snares. We are saying even there we can discriminate. There are some areas that are high risk and some are low risk. And then rangers went out for 6 months and came back with what they found. And where we predicted high risk, indeed more snares were found compared to where we predicted low risk. And this was seen across all of these parks. Today, what we find in Sri Pak Wildlife Sanctuary in Cambodia, these are pictures of the snares that were found because of our predictions. The number of snare captures jumped from 101 to 521, more than 5-fold increase once our system, which is called PAWS, started getting used. This is now in regular use. In 2021, just in March, they found 1,000 snares in the park. And so this is just showing that these techniques that you are all learning about and can be very useful for the fight against poaching. And so today PAWS has gone global. We have made integrated PAWS with the platform called SMART, that is a collaboration with WWF, WCS, and 13 other wildlife conservation agencies. SMART is what is active across the globe in hundreds of national parks by rangers. And so by integrating PAWS with SMART, we've made PAWS available to all of these rangers. We are testing PAWS out in all of the many national parks. And so this is a very exciting time in terms of PAWS getting used in order to make predictions to save wildlife. So I'm going to just say one more thing, which is, there are drones that get used for conservation, and we've built image recognition to automatically detect poachers in these images, human beings who shouldn't be in the park, who are there illegally, and wildlife. So with that, I'm going to stop. I'm going to skip over some of the details and come to the last part, which is key lessons I wanted to repeat. Achieving social impact and AI innovation goes hand in hand. We don't have to sacrifice AI innovation when we try to work on social impact. We want to ultimately empower nonprofits to use AI tools and avoid being gatekeepers to AI technology for social impact. Nonprofits is where we're going to get our AI for social impact problem. It's a partnership. We have in AI for social impact, we have to look at the whole data to deployment pipeline. It's no use just trying to concentrate on improving algorithms because that doesn't achieve social impact. It's important to step out of the lab and into the field. I can give you many instances where sitting in the lab, we had no clue what was going on. And once we went into the field is when the problem became clearer. To embrace interdisciplinary work, whether with social work, with conservation and others. And of course, lack of data, as I mentioned, is the norm. It's a feature of this problem set, and it should be part of our project strategy. So I wanted to mention many of our collaborators who have mentioned, who've been co-authors on the papers I've mentioned. And with that, I'm going to end. And thank you for listening to me, and happy to take any more questions.
Beautiful. Thank you so much for the great talk again. Scott has a question. Do you want to turn on your microphone and ask Milind directly?
Yes. Won't there be a problem that as your model drives success by targeting certain areas with enhanced patrolling, that you effectively drive poachers into other areas, and then that starts to invalidate the results of the model? How do you keep the model trained as poacher behavior changes?
That's a really really excellent question. So first of all, we use a game theoretic model, in order to generate patrols. So the most obvious issue where, if you change patrolling patterns, the poachers will change their reaction. That is taken into account by the game theory. So it sort of is calculating, it's recommending patrols based on this, this calculation. So there's some element of that, which is a very important question you asked, that is already built in. However, if we have learned a model and the poachers now change that behavior, that will indeed become a concern. I have, in Cambodia, for example, after our model started getting used, just before we went to Cambodia to Sripak Wildlife Sanctuary, there was a firefight between the rangers and the poachers. One of the rangers got shot, had to be moved to the hospital. And one reason they told us is because because of the increased patrols and loss of snares, the poachers had become more aggressive. And they wanted to fight back, and so this is clearly a change in behavior that we had not anticipated. So no, these are all very important and interesting open research questions. So short answer is that using game theory, we can handle some, we can anticipate some poacher behavior changes, reactions, but if the poachers completely change their behavior, the learned model gets invalidated frequently, or the poachers actually engage in active deception, then those become very interesting open challenges that are yet to be addressed.
Thank you. That's really great. Just wondering if there's any more question from the audience. Dhirendra.
Thanks, Milind, for the talk. That's really inspiring. I've got a more general sort of question around, working with NGOs. Seemingly AI and NGOs are, as far as you can imagine, on some spectrum of technology use. And how do you sort of bridge this gap? And, what's your experience with engaging with them, talking the same language as they talk? And in general, do you sort of engage in some process of co-development of these models with these NGOs, or what's the process? How do you go about it?
That's a beautiful question. It's a deep partnership that has to be developed. There has to be trust. There has to be time spent in building up a relationship. And for example, with this wildlife conservation organizations, it took me some years just to, initially I was sort of thinking, well, I'll be, sitting in my office in the US, I'll be sending a few emails, and then they'll just say, great, we'll just send you our data and now let's just work together. That's not the way things happen. So this group in Uganda kept saying that you have to come down here and then we can talk. And so finally, initially I was saying, I was sort of reluctant, but then I just flew down to Kampala City. I met with officials there. I went to Queen Elizabeth. Actually, I went to Murchison Falls National Park in that trip and met with people in the park. And then, there was some kind of an understanding, some kind of a relationship that got built. And then after that, I received data from Uganda. Same with Cambodia too. I mean, WWF Cambodia, I mean, they're very interested in working, but they wanted us to see actual situation on the ground. And so we went there, we visited with them, they start, and after that, a very nice relationship got built up, and then we have been working with them throughout. So yeah, I agree. It's not, it takes a little time to build up that trust, build up that relationship. But the end result, I feel, is very powerful, and it's worth it. And for AI researchers, I sometimes I have to sort of drag people out of the lab to say, hey, you have to, you can't just assume that people will just come to the lab and say, here, USB key, all my data, process everything, give me back everything, and then I'll just use it, and wonderful. That's not the way things will happen. And it's true. I mean, they also want to make sure you understand the context in which they're working. And going to Cambodia made us appreciate what a difficult job. I mean, the pay for the rangers, pay is low, poachers are shooting at you. The place is like, I mean, I stayed there in the park for 1 or 2 nights, and it's just like they gave us the best accommodation. And even then it was, I can't imagine how people can stay there for 6 months at a time. They're away from their families. So it gave us a deeper appreciation of the hard work that goes in. And when they say something that saying that, this patrol is hard, we will change our algorithm to make sure that the patrols are better than, what we had given you, rather than just saying, just do it, or something like that. So yeah, it's a very good question. Thank you.
Thanks, Milind.
I'm aware that we've taken a lot of your time. Are you happy to take one more question, Milind?
Sure.
Natasha, would you like to turn on your microphone?
Hi. My question is just around data security and how much you have to focus on protecting sensitive data, in particular in human-focused projects like Oman or whatever.
Yes, no, that's also very important. And earlier we used to work with these the Federal Air Marshals and the TSA and the U.S. Coast Guard, and that was even more sensitive and protected data. Yeah, so these, there have to be very secure protections in place so that there's things that we will not do. For example, we will not print a picture in our papers on here's all the hotspots in Queen Elizabeth National Park in Uganda with a map showing the poachers, where we think their hotspots are or things like that. I mean, those are sort of obvious things, but it's a real concern, and we have done our best to try to protect data. We've gone through, right now at Harvard, we're going through a lot of these negotiations about where the data will be stored, so the university is satisfied that the data is protected and so on. And so we try to go through all of the data protection protocols and everything else to make sure we keep the data protected. So and then try not to put anything, not to make predictions and all these things available easily, not to put them on the cloud, not to put them in the papers, things like that. So reviewers will say, why don't you print a picture of them where all the hotspots are, poaching hotspots are in a national park? We will be, then we can sort of see what is going on. And you have to say, sorry, that's not going to happen. So it's a very, very good question. I don't have a much better answer than that, other than we took, we take data protection protocols of the university seriously.
Okay, thank you.
Great. Thank you so much for the talk. I just have one final question for you. With regards to going to the future. I really like your slides there. I'm just wondering, is there any new way of AI research and innovation that integrates this kind of like societal implications or human-centered behavior into the way we approach the research? Because I mean, I think you started with, many years ago with agents, right? NBDI agents and all those things. But how has these things changed? Because as you mentioned, there's no if you go into the real world, there's no perfect data. There'll be perhaps even data set for you ready to go. Yeah, so what is sort of like, I guess, the key hot future research area in this topic?
Right. So I think one of the things that I feel is a recognition that the entire data to deployment pipeline is important, because when we talk about hot research areas in AI, we often focus on just algorithmic portion. This reinforcement learning is now hot versus something else being hot, etc. And so for at least for AI for social impact, my view is that the idea that we actually have to see impact in the real world is something that will become more important. What this means is that understanding how to efficiently measure impact, how to actually do clever experiments to measure impact. Because these are things like in public health, there's a whole field called implementation science, as you may know, whose job it is to actually measure impact and how to actually, do clever experiments so that you can see differences. Does something work in Australia may not work the same way in Los Angeles, in India or something like that. So these are all questions of culture, context, impact. So these kinds of things we often say, oh, that's not AI, that's just like, somebody doing experiments in the field. But that's science. I mean, that's like testing an AI algorithm versus some other algorithm, understanding why something worked, why it didn't work, all these sorts of things. So that's on the experimental side. And on the data side, I mean, there's sort of this idea that there's so much data, like we are drowning in data. Everybody, guys, but this, in our domains, this is not true. And so we have to come up with all these clever techniques of sampling social networks and, this restless bandit, because we can't quite figure out who's in what state and all of these kinds of things. So these are all outcomes of the fact that we don't have adequate data, and we have to be sensitive and selective and all these kinds of things about data. So at least in AI for social impact, I feel paying attention to the whole pipeline will be an important next step. And I think I just feel like there needs to be, and there will be, a greater recognition that we want to bring AI's benefits to the large sections of the world, who have not benefited from AI. Benefits, have largely been confined to a smaller section of the planet. And in order to actually show that impact in the field and not just write papers about it, we have to actually engage in experiments in the ground and measure impact and deal with the fact that the data are not there and all these kinds of wonderful things. So I think all of these are going to become important. I feel they should become important. Hopeful they're going to be important. So thank you. I mean, that's I guess where I stand.
Thank you so much. So hopefully there'll be days and time in AAAI or those conferences where accuracy is not the goal, right?
That's right. And all social impact is the goal, and you're not just measured on, did you improve the algorithmic efficiency or whatever, but rather, hey, what impact did you actually achieve on society?
Thank you so much. So big round of applause for Milind, and I really appreciate that. Very inspired. I'm sure everyone else is inspired too. So and the talk is recorded, so I'm going to have it uploaded and I'll share it with everyone.
Thank you. Thank you so much. Thank you for inviting me. Bye.
Bye.